This video is the first in a module on two-body problems, specifically central force, conservative force, two-body problems. It's going to be the first major application of Lagrangian mechanics that we undertake to study. And the problems that we're going to look at are can be described as follows. We have two masses, M1 and M2. And the forces between the two are central, that is, that they point towards from one mass to the other. So we have here F12, force on mass 1 from mass 2, and this is force F21, right? So two particles who are interacting through a central conservative force. So if the force is conservative, that means it doesn't depend on direction. So that means that the potential that we can associate with these two particles, U of R1 and R2, as we've seen before, is really just a function of the magnitude of R1 minus R2. If we then define the variable R as the relative position of R1 with respect to R2, that is the vector R1 minus R2, that gives us then that U of R1 and R2 is just equal to U of R, where R is just the magnitude of the vector R. Okay. Well, some examples of this kind of force. We can, for instance, have a gravitational potential. Like that. Or we can have an electromagnetic potential. So that's the potential between two particles that both have charge E. So because both gravitational and electromagnetic potential have this form, this type of problem describes a lot of things that happen in nature. Anything from the hydrogen atom to diatomic molecules to satellite planet systems to systems consisting of a planet and a sun. They're all described like this, with two particles interacting through a central force. Of course, when a third particle gets involved, things get much more complicated, and it turns out in that case we can't solve the problem exactly. But we're going to stick now to the two-body problem here. That we can solve exactly. And we will do that by starting from this two-body problem. It has, as you might guess, 6 independent variables. We'll then reduce that to a single particle problem. That is 3 independent variables, which we then will reduce to a 2-variable problem, and then finally to a single variable problem before we solve it. Okay, so this sketch here shows the relationship between the position R1 of mass 1, R2 of mass 2, and the relative position vector R. We're now going to introduce one more vector, and that's going to be Well, first of all, we should say that r is the relative position. And we will introduce one more variable, which we'll write as capital R. Which you should recognize as the center of mass. So there's R right there. So I promised we'd solve this with a Lagrangian approach. That means, of course, we should write down Lagrangian. So in this case, that's not so difficult. We have U, the potential U, which depends only on R. So we can just say that the Lagrangian is 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared, and then we have to subtract U of R. The next step is now to change variables. So the Lagrangian depends on little r and big R instead of R1 and R2. We actually already know what the result is going to be for the equation of motion in big R. We have a system here of two particles where there's no external forces acting on them. So we really should have that the total momentum of the system is constant. So we should be getting, if everything is working okay, and here I also define one other thing. Capital M is M1 plus M2. So this is what we should be getting in capital R. So let's now see what we get when we make the change of variables. So the first thing to do then is to write R1 and R2 in terms of little and big R. And that's fairly simple algebra. I can just write that R2 is R1 minus R, and then plug into this expression, which I'm going to write in this fashion. And we can see that m1 plus m2 divided by capital M must be 1. Because, of course, capital M is m1 plus m2. So that makes it very simple to solve for R1. This we can then just plug into the expression for the kinetic energy. Potential then is all written in terms of little r, so we don't have to do anything to that. But the kinetic energy, which is this, of course, and of course, we're putting in velocities here, but that's easy to obtain. You just differentiate that, and you get dots over all the r's, because they're all positions. Okay, we can see that this term and that term cancel. And then all we have to do is bring together the terms to depend on capital R dot square and little r dot square. This is equal to m, so it cancels one of those m's. The final result then is that the kinetic energy where mu is m1 times m2 divided by m1 plus m2. This is known as the reduced mass. Okay. The reduced mass is going to be very important to us. So I'm just going to note a couple of properties that it has. So first of all, if one mass is much greater than the other, let's say that m1 is much greater than m2, well, in that case, the reduced mass, mu, is approximately equal to m2. So in this case, it's equal to the smaller mass. Mu is always less than both m1 and m2. So hence reduced. And in the particular case, where m1 and m2 are equal, we have that the reduced mass mu is just that mass divided by 2. It's half the mass of each of the particles that's involved in the motion. All right. So then we have that. Now we have what we need in order to write down the Lagrangian. So let's do that. The Lagrangian for the two-body system here, L, consists of a couple of different parts. So you see I've divided into two pieces here. We have the center of mass Lagrangian and what I'd call the relative position Lagrangian. Now because what we have here is a Lagrangian that can be written as a sum of two Lagrangians which depend on different variables. Because we can do that, this means that the solutions for the motion is completely independent of each other in capital R and little r. In other words, the center of mass motion and the relative motion can be solved as separate problems. Also, we can see immediately that the Lagrangian does not depend on R. Or it doesn't depend on capital R, to be more precise. When the Lagrangian doesn't depend on a variable, capital R in this case, that variable is ignorable. And that means, as you know, that the corresponding momentum is conserved. So that should be the equation of motion in capital R. I can just quickly verify that. So m capital R dot is constant, same thing as saying that the momentum, the total momentum of the system is constant. All right. Now, because of this, because the center of mass is moving with a constant velocity, we can change frames to the center of mass frames That's going to be an inertial frame, again, because there's no acceleration in the center of mass. So if we do that, then capital R is just identically equal to 0. So this gives us that the Lagrangian in that case is just equal to the relative Lagrangian. So what we've done now, if you look at it, we have reduced the two-body problem to what is effectively a single-body problem. Right? This is exactly what we would write down if we had a potential for one particle that was located at position r and that had mass mu. And this is what makes this possible to solve, actually. In the next video, we're going to continue looking at this Lagrangian and find out some more of its properties.